Okay, so this is where we left off in the previous video. So let me go to full screen, bring back the laser pointer. Okay, so we said that our speed up would be basically dependent on the number of stages, and and as we increase the number of stages, we can get better speed up. But the problem is that the complexity of the hardware and the pipeline will also increase with increase in number of stages. So we have to kind of balance between how many stages we want to have and how much speed up we want to have. Now, notice that the improvement in performance that we get because of pipelining is due to improvement in throughput, not necessarily due to latency or the time that it takes to complete one instruction by itself. So throughput, if you remember, is the number of instructions completed per cycle. And latency, if you remember, is the time that it takes to complete one instruction. So if you go back to our comparison between the single cycle execution and pipeline execution, if you just look at the execution of one instruction, for both of them takes 800 nanoseconds, meaning that for the single cycle, an instruction by itself takes 800 picoseconds to complete. This instruction takes 800 picoseconds to complete. This one takes 800 picoseconds to complete, and so on. Now, if you look at the pipeline case, it's still the case. The first instruction, if you just look at it by itself, if you measure the latency of the first instruction, it starts here and it finishes here, and it takes 800 picoseconds to do that. Then the next one is going to start here and it's going to complete here, and again it takes 800 picoseconds to complete that instruction, and so on. So the latency, or the time that it takes to execute one single instruction, does not change whether you are pipelining or not pipelining. What changes is number of instructions completed per cycle. So what happens is, here we are completing one instruction every 800 picoseconds in the case of the non-pipelining, while in the case of the pipelining, we are completing one instruction every 200 picoseconds. So obviously our throughput, or number of instructions per cycle, number of instructions completed per cycle, is much more in the pipeline version compared to the single cycle sequential version. So the improvement in performance is because of throughput, or number of instructions per cycle, and not necessarily due to latency or improvement in latency, which is the time it takes to complete a single instruction. So I hope that that's clear, and certainly you'll have options to ask me questions on Friday when we are back in the class. So now let's talk a little bit about the pipelining and instruction set design, the relationship between the two. Remember that pipelining works really well when pipeline stages are balanced. If they are not balanced and equal, and they're complicated, then pipelining is not going to work as good as expected. So in case of the MIPS instruction set architecture, remember that ISA stands for instruction set architecture, it's designed in a very regular and repeated manner. So for example, in MIPS, all the instructions are 32 bits long, and they pretty much have very similar formats as we have seen already. So that makes fetching of an instruction really easy, and that makes decoding of an instruction really easy, because we know exactly where the opcodes are. We know that we only need to get 32 bits to get an instruction. And because these are fixed, then we can do this very efficiently. Now, in comparison to MIPS instruction set architecture, consider Intel's x86 architecture, which has the number of instructions in x86 vary from 1 to 17 bytes per instruction. So that means that some instructions are 1 byte long, some instructions are 3 bytes long, some are 17 bytes long. So you can kind of imagine that the fetch cycle now becomes very complicated because you have to figure out how many bytes to fetch for the next instruction. In the case of the MIPS, it's really simple. It's only 32 bits. We know that we only need to get 4 bytes, and that's easy to do. In the case of the Intel x86, the hardware becomes much more complicated because now we have to have exceptions for different instructions. So that's why pipelining fits MIPS architecture really well. Another thing that we already touched on is that when you have few and regular instructions, then the decoding and reading of the registers become really easy. Again, if you go back and remember the instruction formats in MIPS, they all have the same bit positions for opcode and for function code when function code is needed, and therefore decoding is really easy. And also we know where the registers are specified in an instruction, therefore register reads become very easy. And because both of them are easy, then we can kind of put them together and carry them out in the same step. So that's another thing that MIPS has done in order to make its architecture more suitable for pipelining. Load and stores are also very interesting because we separate calculation of the address of the memory from accessing the memory. So we calculate the address in stage 3, but we access the memory in stage 4. So the advantage of doing it this way is that memory accesses become very efficient and they can be carried out only in one cycle. So by basically doing the alignment as well as shifting of the offset and adding it to the base in the third stage, we have carried out all of those operations and the address is ready for the next stage. Therefore, during the next stage, we can access the memory right away. If we hadn't calculated the memory address in stage 3 and we go to memory access becomes complicated because now we have to calculate the address of the operand first and then access the memory. So by this separation, we are making memory alignment and access to the operands much easier and within one cycle. So all of these decisions that have been made in terms of the way that MIPS data path is designed is all geared towards making the pipeline operations as efficient as possible. So now let's move on to the next topic and talk about this a little bit before we end this lecture, and that's hazards. So far I've been giving you a kind of a rosy picture by saying that, okay, so at this cycle we can get the first instruction, and then in the next cycle we can get the next instruction, and the next cycle we can get the next instruction. And if we do it this way, then we can complete one instruction in each cycle once the pipeline fills up, right? So the problem is that things in real world are not that easy. And because of dependencies and issues that come up, we can't always just automatically fetch the next instruction during the next cycle. So let's take a look at these hazards and see what they are and what we can do in order to resolve them. So the hazard is a situation that will prevent us from starting the next instruction in the next cycle. In other words, We can't just automatically go get the next instruction and put it in the pipeline for execution. So there are three kinds of hazards. One is a structure hazard, which takes place when two operations, two instructions, needing access to the same resource, to the same structure. So, for example, both instructions are trying to access the memory at the same time, or both instructions are trying to access the ALU at the same time. So obviously we can't do that, and we have to delay one of the instructions. And then the second thing happens with data hazards. That's when the results of one instruction is going to be used by the next instruction. And if that's the case, then the next instruction has to be delayed until that result is written into the registers, and then it's available for the next instruction to access. So this happens because of the dependency between instructions due to data read and writes. And then finally, the last hazard happens because of control operations for branches and jumps. And again, whenever we have a branch, we have a problem because we don't know whether the condition is going to be true or false. And therefore, we don't know when we can get the next instruction as a result of that uncertainty. So let's begin with the structure hazard. This happens when we have a conflict for use of a resource. So, for example, in the MIPS pipeline, if we assume that we only have a single memory for both data and instructions, then we have a problem because we can get into a scenario where we can access the data for load and store operations, and then at the same time, we want to access or fetch the next instruction from the memory. Obviously, that's not possible. We can't, in the same cycle, we cannot get the data and the next instructions both in the same cycle. So when that happens, then we need to introduce what is called the stall or a bubble into the pipeline. So what does that mean? So let's say that we have this pipeline. We get the first instruction, it goes through, and then the second one, the third one, and the fourth one. Now, let's say that we only have one memory unit for both data and instruction. So what happens is when we get to stage 4, we have a situation where instruction 1 is trying to access the memory for data, and instruction 4 is trying to access the memory for instruction, both of them at the same time and in the same stage. So obviously this is a problem, and we can't do it this way. We have to delay instruction 4 so that instruction 1 would complete its memory operations, and then instruction 4 can begin its operations. So that will mean that we'll have to introduce a bubble into the pipeline by delaying the fetch of this instruction so that now we resolve the dependency of that resource, which is the memory. Okay? So in MIPS, in order to solve this problem, instead of using one memory unit, we use two memory units. So we have one data memory and one instruction memory. And by separating the instruction memory and data memory, now we can have a situation where we can access the data memory for instruction 1 and at the same time access the instruction memory for instruction 4. And in that case, this would be okay, and we don't need to introduce a bubble in the pipeline. So I'm going to stop here. This would be the end of the lectures for Wednesday, and we are done basically with this lecture. And when I come back on Friday, we'll remind you of this, and we'll get into the data hazards.